right, good morning, and where I'm located. This is the last of 4 webinars on flow 2D modeling of hyperconcentrated sediment flows. And this is going to be the culmination of everything that we've done over the last 3 weeks, and it'll include the two-phase flow modeling. So in this one, we're going to talk about two-phase flood modeling for mud flows and tailings dam breaches. And all of the well, Karen just went over all this stuff, so I don't need to cover it again. But what I do want to say is that if you want to review anything that I'm talking about today regarding sediment transport or the mud flow component or how to generate sediment for a mud flow, go back to these 3 previous PowerPoint and video webinar videos that I made Karen posted for the last 3 weeks. Now, before we get started, I want to make 2 corrections. One is on the overland sediment yield using MUSLI, the modified universal soil loss equation by the NRCS, or the RUSLI, which is revised universal soil loss equation. And in the previous webinar, I discussed these and the yield in terms of tons per acre per year. And Henry, one of our users and webinar participants, corrected me on this. And I have used the modified universal soil loss equation in the past, and I just assumed that RUSLI was an update to it, not having used it. And it's not exactly an update. It uses a different rainfall erosion factor, and it'll give you the reported output in tons per acre per year. But the original modified soil loss equation only gives it to you in tons per year or in tons per acre. So you can do this on a prescribed or a specific storm basis. You don't have to do it on an annual basis or get an annual estimate from this and then try and convert it or make some assumptions to use it. So what I'm saying is that use the modified universal soil loss equation if you're trying to replicate a storm or do a 100-year event or something like that. So if you use MUSLI, you're going to get this in tons per acre for fire prescription and for post-fire and so forth. Okay, and here's a reference if you wanted to look at the differences and discuss and look at the application of the RUSLI. And the other clarification that I wanted to make, it's not so much a clarification, but just a highlight. I talked 2 weeks ago about mud flow laboratory analysis and how to get them. And we had a question about the shear rate for this. And then I discussed with you the potential to use a different types of commercial viscometers and so forth. One thing that I failed to mention, or that I might have mentioned, but let me highlight here, is that you need to run any commercial viscometer or any laboratory viscometer on the same order of magnitude that you would see in the field conditions. So if you have a rotational viscometer and you have the number of RPMs and you're measuring the shear stress based on those RPMs, the RPMs, you have to limit this to a certain amount, a certain speed, so that you don't get slippage. And you can see it in the data. So this is like one sample that I'm doing for one concentration by volume, and I'm trying different speeds. And as I increase the speed, I measure the viscosity, but based on the slope, which is the viscosity, I make these measurements of the shear stress. Based on these different speeds, I get this plot. But at some point, you'll start exceeding the actual laminar flow in the rotational viscometer, and what you'll just get is slippage in a boundary layer or near a boundary layer, and that slippage will be very evident. you'll see it here. And so you have to limit this to about 10 inverse seconds. So if you went out and did an estimate in a stream bed and measured the velocity or estimated the velocity near the surface, knew the depth, you would find that you would probably be under 10 inverse seconds. On the other hand, if you crank up your viscometer on the order of hundreds or even thousands of RPMs, which some people have done, all you're doing is getting slippage between the layers. And if you want to measure the viscosity, this has a much higher viscosity than this does. And this would lead to an inappropriate estimate of the yield stress if you projected this down. So if you did everything above 10 inverse seconds here, you would not get realistic data that would replicate what's going on in the field. Okay, so those are the two highlights that I wanted to make from the last two webinars. Now, today's webinar, I'm going to talk about two-phase flow, and we now implemented the two-phase flow for channel flow and everything else in the model. So this new update will have two-phase flow for everything that was in the Flow 2D model. Previously, there was a two-phase flow model for just tailings dam, and I called this flow two-phase.exe was the executable, and it was just for overland flow. Now we've done it for the channel, and so I'm going to talk about that here today. Now, with Flow 2D and previous versions of the model, there was a couple of limitations. One is if you did conventional sediment transport, that is, suspended load, bed load, the total bed material load, you would be doing this analysis for concentrations by volume up to about 10 to 15, 20% concentration by volume. And all of these analysis that you would do would be essentially water behavior, meaning that it's turbulent, highly turbulent flow. Particle fall velocities are more or less what you'd see in water and so forth, but they would ignore the viscous and dispersive stresses for sure, and you would just be modeling turbulence as a turbulent velocity profile. On the other hand, for mud flows, if you were to model only mud flows without water, just hyperconcentrated sediment flow, there's no exchange with the bed. That is, it's just a flow that would either cease flowing and be remobilized, but there's no bed exchange. There's no scour and deposition. And the reason is that there's you can't predict the fall velocity and drag in viscous flows with particle collisions. Nobody's really done that. Well, as far as I'm aware of, nobody's really done this so that it has practical application in a fluid model. So in this case, what I'm going to do for you is to integrate fluid flow and mud flow in the same model simulation. And the sense of this, or the stimulus for this, came from modeling tailings dam failures at water storage, because if you have water storage and you have an instantaneous breach of the tailings dam, the water would drain out first, and then with some of the tailings, but most of the tailings would then ooze out or come out, and the water flooding would race ahead of the mud flows, and so we were really unable to model that effectively. So the idea is that I put this in initially just for tailings dam. I put the two-phase flow component in for tailings dam, but now you can do it with any kind of mud flow, in like channel flow, where you might have a mud flow going down the channel and having a tributary enter downstream with water flow or conventional sediment transport. So let's start with the typical mud flow. And if you're going to do a typical mud flow with Flow 2D, you would switch on the mud switch in the control.data file. Excuse me. You would turn off the conventional sediment transport switch and any kind of just general generic bulking factor in CONDOT data, and then add the M line for mudflow in SEDDOT data, where you add the coefficient and exponent for the viscosity, coefficient and exponent for the yield stress as a function of concentration, and the specific gravity if it was different from sand or whatever. And if you wanted to enter a K laminar flow resistance coefficient, you could enter it here. And when you did that, you would have you would also add the third column in the inflow hydrograph, so that you would have time and discharge pairs, and then you would add a representative concentration by volume. And I discussed with you last week on sediment yield and sediment supply a little bit about how to distribute the concentration in a typical mudflow hydrograph. Now, as an option, you can also enter just the volume directly in above the fan apex. Again, I discussed this last week, but you could enter the volume in cubic meters or cubic feet, and then you could route it downstream. If you entered this just 2 or 3 elements upstream of the fan apex, you would just load it, and then it would start tracking this volume downstream in time and space in every grid element. So a typical flood and mud flow hazard scenario would consist of, in this case, maybe water flooding, low concentration with bulk flows, maybe 20% or something. Just use the X concentration factor. You're not going to model the hyperconcentrated fluid behavior. You're just going to bulk it. And then if you go on to mud flows where you have a variable CV, then you're going to actually model the fluid behavior as it moves downstream, and then you can add all of the details to it. So in the flow 2D mud flow routing, the fluid properties are going to control the flow hydraulics. It treats the fluid as a continuum, and you can cease flow or remobilize it if you had at a different time water entering a specific grid element that was had a smaller sediment concentration or no concentration at all. And the model tracks the water and sediment volume on a cell basis, which would dilute the flow in some cases. So the typical products here would be a maximum depth, possibly from a dam's tailings breach. And if it ceased flowing after a period of time, you could look at the final depths and see what they were. Now, let's discuss the two-phase flow component here. And what I've done is, what I'm not capable of doing, let me start that way, is that I'm not doing Lagrangian particle dynamics here. I'm not tracking individual sediment particles, computing the lift and drag on each particle component, getting a mixing zone and having the particles cross the mixing zone. I'm doing gross volume finite difference modeling of the fluid sediment transport on a cell basis, and then the mud flow, which would typically be under the fluid phase separately, and then I'm exchanging between the two. So the idea here is that the velocity profile, would look like this, perhaps, where you'd have the mud flow kind of shearing along the bottom here with a more or less a uniform concentration, and then have some vertical velocity distribution in the fluid volume, and then have the concentration by volume profile look fairly uniform up into the fluid transport, at least across or near the boundary here, and then you would diminish this towards the surface. So what I'm trying to do here is to give you a tool that would give you an idea, that would enable you to predict roughly where the fluid would inundate an area from a tailings dam breach, or just a typical river flooding, as well as showing you where the mud flow may cease flowing, as well as having the sediment be exchanged between the mud flow and the fluid phase. So in the upper fluid phase, I'm still doing the conventional sediment transport processes using the choice of 11 sediment transport equations. In the lower sediment layer, where the viscous stresses are controlling the flow, either as a mud flow or a mud flood perhaps, this is moving along under the fluid phase. And then there isn't a sediment exchange between the two layers, and I'll discuss this with you. There is potential flow cessation of the fluid phase, and then you can have scour and deposition from the mud flow to the fluid phase, or between the two phases, or if the fluid phase outruns or outdistances the mud flow phase, then it contacts the bed. The mud flow layer is missing, and you can have bed scour and deposit on that phase. So the overall flow processes would include mud flow cessation and remobilization, the fluid layer racing ahead over the mud flow layer, as particularly in the case of a tailings dam breach. The fluid layer can pick up or drop sediment to the mud flow layer. It increases or decreases the sediment concentration in each layer, both the fluid layer and the mud flow layer. The mud flow layer can become more dilute because it exchanges particles into the fluid layer. The fluid layer can become part of the mud flow layer because enough particles are gone, or enough water has raced ahead, and the fluid layer concentration has increased to the point where it's essentially a mud flow layer. And if the mud flow layer ceases to exist, then the fluid layer can exchange sediment with the bed with scour and deposition. So conceptually, the way this occurs then is we're computing the sediment transport using sediment transport capacity equations, which in reality don't apply for hyperconcentrated sediment flows because most of them are based on river flows or flume experiments, but they can certainly extract or extrapolate into higher concentrations by volume, given that there's an unlimited supply of sediment and a steep enough slope and velocity or other attributes of the flow. And then on the lower layer, the mud flow layer, it can cease if the slope, becomes more mild, or if the concentration increases because it's there's an exchange between the bed and or between the fluid and the mud flow layer. It becomes either more or less, the concentration changes, and so it could cease mobile, or it can remobilize. And then finally, if the fluid layer races all the way ahead and is not any further in contact with the mud flow layer, then it will exchange sediment with the bed or the ground directly. Now, we talked about all of this in the previous 3 webinars. We talked about the conventional sediment transport. We talked about the mud flow separately. And so I'm not going to go back over those. If you want to, if you're new to the webinar series today, you'll need to go back over those previous 2, the first and second webinars, in order to gain more knowledge on the conventional fluid sediment transport and the mud flow, hyperconcentrated sediment flows. So, but in this one now, with the new channel 2-phase flow, we can have fluid flow down a tributary like water into a channel, and have mud flow coming down a river channel from upstream. And it might be from a tailings dam breach, or it might just be a natural mud flow that entered off an alluvial fan coming downstream. The fluid flow could enter this channel in advance of the mudflow hydrograph, or during or after. So in this case here, the fluid flow, this is a very simple example I did. It has 1 to 10, 0 to 10 hours, only up to 1 cubic meter per second, and just a conventional sediment load of 5% concentration by volume. And you can see that it starts entering this at around, well, just after a 1/10 of an hour. So it gets up to flowing full at 1 hour. So at 1 hour, you've got flow going down the main channel. In this case, the mud flow, which is entering the channel at 45% concentration by volume, it does about the same thing, but at a 1/2 an hour, when this is already flowing at 1 cubic meter per second, is the time when it starts to ramp up to 3 cubic meters per second at 45% concentration by volume. So in this case, the water is already in it. The water comes down this channel, goes up the channel a little bit, and then the mud flow contacts it. And then you get both overbank flow, return flow, and combined flow downstream. And this is what it would look like if you ran it out in terms of the maximum floodplain and channel flow depth, regardless of whether it was fluid flow or mud flow. But here you see some of the mud flow coming over bank. This happens to be a rectangular channel, not very deep. This happens to be a trapezoidal channel, just to show that you could mix and match channels. And that I could test it appropriately. And this is fluid flow that's overtopping the channel, and it has a concentration, but it overtops the channel of 5% or something. And then it runs down, it drops some of its sediment, runs down overland and enters the mud flow filled channel here, whereas this is all mud flow overbank flowage up here. So let me give you some rules for this, and then I'll show you the tailings dam breach representation of the two-phase flow. So rules for the computed fluid exchange. And this is the essence of what I've done. And again, I realize that this is fairly simplified. I also realize that, you know, quote, it's not, quote, a directly two-phase flow analysis where I'm doing all of the particle dynamics on water and sediment particles to enable me to call it a two-phase flow in that regard. I mean, if you're going to do two-phase flow, you might as well do it for a small feature and do do it in 3 dimensions, and there are some models out there that do that, but you're not going to do a better job necessarily on trying to compute the overland flow, flood inundation, or where a mud flow starts and stops using a lot of very highly variable lift and drag coefficients and viscosity variations, as well as inhibited fall velocities from particle collisions in a very detailed model like that. And I mean, it's just too complicated. So the concept here is to simplify this so you get something reasonable, so you can get people out of flood areas downstream of tailings dam breaches and so forth, or mitigate them and mitigate the damages or something like that. That's what the essence of what I'm trying to do for you here. So these are the rules that I have in these, and if you want to debate these with me, you're welcome to. If you have a fluid phase, and when the fluid phase gets greater than 30% concentration by volume, the fluid layer, sediment, and water volumes are completely added to the mud flow layer. If you have a fluid layer that's greater than 20% and the mud flow layer is less than 56%, then the fluid layer greater than 20% is directly added to the mud flow layer. If you have a mud flow layer that's 56%, then this just goes into the bed and stops flowing. If you have a mud flow layer that gets less than 20%, then the mud flow layer sediment and water volume, because it's tracking separately in every grid element, the volume of sediment and the volume of water, and you take those out of the mud flow layer, add them to the fluid layer, and then you're modeling it all as conventional sediment transport. If it's greater than 20% and it's no mud flow, then the fluid volume um, greater than 20% is then exchanged with the bed. So as well as you have scour and deposition. But in this case, if it goes over 20%, I'm saying that we're going beyond the normal scour and deposition. We're going to deposit anything that's over 20% directly into the bed. So these volumes are going to be, these are really small volumes. I mean, we're not exchanging like a foot of sediment at a time or something like that. We're talking about on the order of a second, which means that you're dealing with something on the order of less than 100th of a foot exchange. So it's not, the exchange is not impacting the flow hydraulics for the next time step. And so all of the hydraulics are uncoupled from the sediment transport. And I can do that because the Flow 2D model is so inefficient. It has to run on really small time steps. And just as a reminder here, if people are talking in other papers and so forth about concentration by volumes that are higher than 50 to 60% concentration by volume, they're talking about they're not talking about fluids anymore. They're talking about landslides, or they're talking about ground because you walk on this. um, these are maximum packing factors for spheres, Bagnall's maximum sediment concentration for mud flows is on the order of about 60%. I mean, if you're going to get high concentrations, you've got to have separation in the flow, and that causes the concentration to go down. So everything that I'm talking about here in terms of this two-phase flow and all of these rules that I've imposed have to do with this graph, which I created in a laboratory analysis of mud debris flows by taking tons of different samples, not tons, but a number of different samples, and putting them into a almost like an aquarium, and mixing them and sloshing them around and so forth, knowing the concentrations by volumes and so forth. And so this is how I arrive at 20 to 30% concentration by volumes when I talk about that for mixing, and how I arrive at 56% concentration for mud flows that cease flowing and so forth that become landslides. Okay, so to run the two-phase flow model now, what we've got going for us here is we have to assign two new parameters. Well, actually only one. The mud flow component control, instead of being 1 for mud flow or 0 for no mud flow, it now has a 2 for two-phase flow. And then you can set this to 0 for this conventional sediment transport, because this switch here will turn on the conventional sediment transport in the two-phase flow for you as it's needed. Okay, so you don't have to worry about that. Just turn I set equal to 0. Now, if you're going to do a tailings dam breach, this is where you assign the global concentration by volume. This is the concentration. This is the bulking factor, but I made this so that you didn't have to have more variables and extra data. This is where you would assign 0.45 or 0.50 as the concentration for your tailings and stored behind your tailings dam. Then you need the sed.data file. So in this case, instead of just having the mud flow for a typical mud flow model in Flow 2D, you have both the mud flow and the sediment transport flow, the S line, the C line here. C for sediment transport. There was a reason why I had to do that as a C instead of an S, but I've forgotten what it was. Then you can add, if you wanted to route sediment by size fractions, you can still do this. And you can, if you have size fraction for your two-phase flow fluids, you can do this. You can add this too. And then you can add a scour depth limitation, which may be necessary if you contact the bed with the fluid layer. And some of these equations will, scour like crazy if they get a chance. So you might want to limit it to 10 feet or something like that so that you can control it a little bit. Now, for a tailings dam breach, you want to, there's a couple of different approaches here. First of all, you can do the tailings dam with just the mud flow component by itself, in which case you're not going to do any breach of the dam itself. Maybe you'll use the tailings dam tool to estimate the hydrograph out of the tailings dam breach, use just mud equal to 1, and for the tailings breach discharge out of the dam, and there's no water storage. Or you use the two-phase flow, and now you can do the tailings dam breach with water storage behind it, and you can use the tailings dam component to try to estimate the amount that's actually released through the tailings dam and compare it. So if you're doing this two-phase flow and you're going to actually breach the tailings dam, you can do this with, and I'll get into this in a moment, you can use the two different breach components for dam breach components. You can assign the water surface elevation, and there's two options for doing this. You can assign the original bedrock elevation, meaning that before the tailings dam is deposited, you can just assign a value for the bedrock or the topography, and then the tailings dam elevation will be added to it. Or if the tailings elevation is known because it's level and the original bedrock elevation is unknown, you can just assign this onto your topography and get the tailings elevation. So, and then in the end, if you want to, as you simulate this tailings dam breach downstream, you can have the tailings mud flow movement downstream mixed with any river flow that may be flowing or with tributary inflow, as I mentioned to you. So you have these two choices. Well, you want to assign two things. One is you want to assign the starting water storage, which is this yellow line here, and assign the starting tailings dam storage elevation here, because you have the bedrock elevation is known. And then this is just the dam elevation and so forth, which you'll assign either with the levy.data file or the breach.data file. So the tailings dam level inflow data base requires only one line in order to do this. Bear with me a second here. I wanted to see something. So let me go on. Here's what you're going to assign in inflow.data is an R line for reservoir. Give it one cell somewhere in the middle of the reservoir or near the dam, but inside the reservoir. Assign the water surface elevation if there is one in the tailings dam, and assign either the tailings dam thickness or the tailings dam surface elevation. And then you can assign this is optional, but I just use a base value of 0.2 here for the reservoir, and that's so that you can route flow using the Manning's equation in a ponded situation in a reservoir, because you don't have a turbulent velocity distribution profile when the water just starts to move initially, and so there's no way to get 1 foot per second velocity, average velocity in the vertical profile if you've got 20 feet of flow depth in the reservoir using Manning's equation, because what you're going to wind up with, unless you use a high enough N value, is something on the order of 50 feet per second right off the bat, and the water's just sloshing around in the reservoir. because you've got a finite, you've discretized the surface into finite grid elements. And so the minimum elevation difference between the water surface elevations might be a thousandth of a foot, but that's a fairly steep slope when you're only dealing with maybe 10 feet or 20 feet or something like that. So the idea here is apply this and you'll get reasonable velocities in your reservoir as the reservoir drains. This is more necessary for filling the reservoir than it is draining the reservoir, but it still works. So you can do this, or you can actually um, uh, also assign a tailings dam.data file, and the bed elevation is the tailings dam elevation. In other words, your elevation database is um, the tailings. The topography you have is the actual tailings of the reservoir, and what you want to assign is a tailings thickness below that elevation. And so you can enter this as variable 10, 9, 20, whatever, and that will then define the topography below the tailings. So you'll have this additional opportunity. Sorry. So here's the way a typical tailings dam um, project might look. There's actually, in this case, it was actually 2 tailings dam that a client was using here, and they gave me this project and I asked some questions about it, and I just filled only this reservoir as an example project, but they were filling this reservoir, breaching it, and then seeing if this one overtopped or breached or whatever. And this is the same one that I used with the channel in it before, so I could put the channel back in it and have the channel inflow to it. But I wanted you to see this occur a little bit more simply so that you would understand what the model is doing with the two-phase. So in this reservoir, I have a um, water surface elevation and the tailings elevation. So in this case here, you can see if I zoom in inside the reservoir, when I ran the model, all of the elevations from around 75, 76, which is right here, are all getting assigned the same value for the water surface. And then for the tailings dam here, this surface layer here, um, this is the actual tailings dam mudflow surface layer. Let me see if I zoomed in on that. Yeah, I did. And you can see that the mudflow layer inside assigned the 76, 75, 76, which is, no, it's over here somewhere. But you can see that they all assign the same tailings elevation. So I had the topography of the tailings dam original surface below the tailings. So then I have to make some revisions to the data files. I have to assign my mud equal to 2 for two-phase flow. I assign the concentration to some value here for the tailings, saturated or otherwise. I assign the R line, which I just showed you in the previous 2 slides, and then I combine some data for the M lines and the sediment concentration, sediment transport capacity lines here, and then this optional one if you needed it. So you run the model, and then when you do that, you get some new data files. You get maximum fluid and mud flow sediment concentrations, final fluid and mud flow concentrations, max fluid, mud flow depths and velocities and so forth. And I created new max plot programs and profiles programs so you could quickly review this, and then you can plot all the details with the nice pictures and so forth, background images and everything in QGIS or in Crayfish or whatever, and Mapper, and that's for Karen to show you how to do that. So I'm going to run this example. And what I've got in this particular example is 5 meters of tailings at the dam, 3 meters of stored water. I'm going to assign an initial water saturation of the tailings of about 40% concentration by volume. So there's still some air in the pore space of this, it's not completely saturated, but it's close. And I'm going to And then when you run the different simulations here, I'm only going to run one. In this case, it's going to fail instantaneous to the bed using prescribed breach. And typically this would be preferred for maybe a worst case scenario of releasing everything at once. But you could also fail this by erosion using the dam breach modeling, where it actually erodes the dam, or fail it by prescription breach rates. And then if you did that, you can assign an individual sediment transport equation to calculate the sediment transport out of the breach due to the water flowing over the mud flow as the breach eroded. So as the water goes through the breach, it erodes from the mud flow surface and increases the concentration downstream. So I'll run this for you and then we'll look at some results here. I have to get out of this and run it here for you because I couldn't make the graphics resolve itself with this duplicated screen. So here's the tailings dam. Here's the breach. Start of the breach. It's got a pretty good floodway movement, and it's the water coming out of the mud flow. The mud flow is coming out also now by this time because it's eroded all the way down to the mud flow layer already. So some of this is now two-phase flow as it's moving downstream. So I'll just run this for a little while for you. I actually ran it for 24 hours and then you'll see the results. So I'm not going to run it for the full 24 hours. We'd be here about 5 minutes or so. But maybe not that much, but I just wanted you to get the idea of what's going on. Now, if I did this in the channel, it would be entering the channel, and then I could have this little tributary channel coming in with water here, further diluting the flow on this two-phase flow. Where's the mud flow at this point? It's probably somewhere in here, and the water's running over it, and it's picking up sediment and moving it downstream with the conventional sediment transport equation. And I'll talk about, which equations you might use appropriately to develop some other scenarios. So you can see now that probably most of the water has drained from the reservoir here. So this is what's happening. It's taking sediment off the mud flow layer. The mud flow layer moved out. It's taking sediment off the mud flow layer here. If there's any water left, most of the water is already downstream here. The mud flow layer, as it's drained of water and as the water is drained out of this, then the mud flow layer is viscous enough that there's going to start, as the water pulls out more sediment and increases the concentration, this will cease flowing. So we get down here to the bottom and it's completely flat and it runs to the outflow element, ponds or whatever down here because there's no, this was following the general line of the channel, even though the channel was not in this model per se. The topography existed for the dry channel more or less, and so it followed the channel down. So we're at hour 3 roughly here now. It's running pretty fast, but I'm going to stop it because there's really not much else to show you with that. So let me go back to the PowerPoint presentation and we'll take a further look at some of the results here. And all of these are just max plots. I mean, I could make this look pretty and plot it on some aerial imagery or whatever, but I want you to get a full sense of, what's going on here. I don't need to show you high resolution graphics. That's just a simple tool that people create to make things look nice. It doesn't have anything to do with the flow properties and so forth. So I did this for a whole 24-hour simulation. It's an instantaneous failure after 0.2 hours, and you saw that. And I used the Zeller-Fullerton sediment transport equation, which kind of gives you moderate results for this concentration, or for the conventional sediment transport load. So maximum depths, let's take a look at these first. So we had, for the maximum fluid depth, we had all of the flow filling the reservoir here up into the upper basin parts of this, and then all the maximum flow depths, regardless of occurrence as the flow went downstream. For the mud flow depths, the maximum mud flow depth after 24 hours only made it this far. The water went on ahead, raced over it, dragged out some particles out of the mud flow, and this stalled and eventually. So this was the maximum mud flow layers behind the tailings dam, with a little bit into the upper basin where the elevations were a little bit lower than the um, uh, mud flow depth, and they're just barely below the tolerance in here. So that's why it looks like that. So the final fluid velocity after 24 hours looks like this. I mean, you have, um, you know, um, the the flow depth is still pretty high in some holes and so forth downstream where you have adverse slope conditions and so forth, but it's barely moving. So there's still a little water moving downstream. It's dribbling. There's a little bit of water moving around in the reservoir, but it's essentially stopped. And this is just, the fact that it's, you got a little bit of, you're right at the tolerance value, and it's just going higher and lower, and it's slopping around in there a little bit, but it's hardly moving. And then for the mud flow depth, final depth. So there was still some mud flow tailings retained behind the tailings dam breach when it hit the bottom. And this is not moving at all inside the tailings dam. There's a little bit of mud flow seeping or oozing along downstream here, just barely, but after 24 hours, all of this would be essentially deposit. Now, is this exactly, you're going to get exactly 3 feet of deposit or 3 meters of deposit here? Probably not. I mean, but the idea is that you're going to get something that's representative of the area of inundation for the viscous stuff up here and for the fluidized stuff down here. And it's going to be about as accurate as you can do because you know the volume in the reservoir. Because you know the volume of the reservoir, this is the best any hydraulic model can do. If the model conserves volume, you can roughly predict the area of inundation fairly well. And so, whether this, extends a little further downstream or more deposits up here depends on your initial saturation levels, and if you did any laboratory analysis or you're just using the mud flow parameters here, whatever it is you did, you're going to see some variability in this. But in the end, you're going to say that, if there are people living in homes, maybe here and here and here, along this channel, and you've got a tailings dam up here, I'd get them the hell out of there. In terms of them living up here, well, and this breaks, they're finished. I mean, the the, the bottom line is you should exercise some degree of caution and conservative approach to doing this so that you can ultimately mitigate the issue. Now, just to show you that we were somewhere on the order of appropriate concentration by volumes, we got up, but most of this is between um, 10 to 20% concentration by volume. We got down here, all the sediment drops out on the flat part, and you have no sediment concentration in your cells that even got inundated down here. So this is certainly within the range of the fluid. For the mud flow, we're somewhere in the range of, we remember we started at 40%. Some of these went up to 50% because why? Some of the sediment got picked up and moved downstream, and it stopped flowing when it got up to on the order of 45 to 55% concentration by volume. And that's what physically you would expect. For final sediment concentrations, most of the sediment is, once the water has stopped flowing, drops out. If there's a couple that are barely moving at all, you might have some limited concentration by volumes still in the moving part. Um, for the final sediment concentrations of the mud flow, you have this because it stopped, it ceased flowing. So there was some bed scour deposition on the actual bed itself due to the fluid layer contacting the bed. And you can see that here. Um, blue and green is scour, red is deposition. And so what you're seeing here is what you would expect, waveforms moving in the bed downstream. You have scour and deposition, you have scour, deposition, scour, deposition, scour, deposition, just like motor vehicle traffic on a highway. It's my favorite analogy. With the mud flow cessation, you can make yourself one general bed change plot if you wanted to, where the mud flow depth is added to the scour depth and uh, uh, the bed scour and deposition from the fluid, and you can see the overall um, change in bed here. So you do get some scour downstream from the fluid, even though you have most of the issue is sediment deposition. You can still have some lowering of the topography where the water scours. Now, this is a lot of information, and I'm not expecting you to read this. I just gave it to you for the purpose of when you review this PowerPoint presentation and you're running your model, it gives you an opportunity to look at what you should be reviewing in your project results in terms of model stability. Did you conserve volume? Um, look at maximum velocities, maximum sediment concentrations, whether you're getting any scour and deposition, and a little bit about what to do if your results don't appear to be what you might think is appropriate. Like for final bed scour depths are excessive, select another equation or assign a reasonable scour depth limitation, etc. So you get the idea. So that's just for your edification. I do emphasize again that Flow 2D conserves volume. Um, in the summary.out file, reports on volume conservation. In this particular simulation here, we have stored water, tailings water content. Um, we have bulk tailings water plus sediment, and then total volume. It matches the total volume plus storage, total outflow volume plus storage here exactly. It's very good. I pride myself in the fact that my volume accounting is very accurate in Flow 2D, even with complex two-phase flow models here. I certainly advise you, if you're using any other model, especially HEC-RAS or any other model, to watch this carefully, because this can impact the area of inundation downstream, especially if you get in, this is in cubic meters, but if you have 100,000 acre feet stored behind a reservoir and you're only conserving volume within 1% or so, that becomes 1,000 acre feet volume of water that you're not accounting for or over accounting for. So this is really critical, because the idea here is the volume pretty accurately from the stage in the dam or reservoir or tailings dam material. And this can define for you pretty accurately what the maximum area of inundation is. And in this case, this isn't going to always be true for the sediment volume. This is a little bit more um, uh, subjected to the scour and deposition and channel and where the cutoffs are and so forth. In this particular model, I didn't have any cubic meters error of volume, but if you had a few meters, cubic meters, or just a thousandth of an acre foot of sediment volume conservation error in the model, I wouldn't worry about it too much, because it's not changing the overall hydraulics and you're still conserving the actual fluid volumes. I'll try to improve upon that as time goes by, though, if necessary. And if you point it out to me, if you get some runs that are a little excessive, let me know. So recommendations on tailings concentration. Well, but one thing that I would do, because it's cheap, is go to your tailings. And most tailing mining companies do this, is they go out their tailings and get samples and do laboratory measurements on their samples. They might even do viscosity measurements for you. I've seen that in a couple cases. Excuse me. So I would certainly measure moisture content and size fraction. And typically the saturated tailings are going to be between 40 and 50% concentration by volumes. If they're very dry with no water sitting on the surface, they can be slightly higher than that. In terms of sediment conventional fluid sediment transport capacity relationships, I would try 3. I would try like something on the order of Engeland and Hansen, moderate, Meyer, Peter, Mueller, Smart, low, Cream, Kennedy, or maybe Yang's or somebody like that. But I talk about all of these in the conventional sediment transport webinar that I did at the beginning of the start of this series. So I would try at least 3, but you can refer to that because I describe each one of those in the webinar. Now, as far as an approach goes, I would start simple, of course, and then develop a worst case scenario. So you start with water, and you first you develop your hydrology. You need an inflow hydrograph or maybe a PMP to your dam breach model, or maybe it's just a sunny day failure. It could be either one. In terms of the dam breach, you can do instantaneous or prescribed rate. I recommend those. You can also do the erosion breach modeling, and there is a typical dam breach webinar and PowerPoint presentations for this. You just have to search around on the website for it. Start with reservoir water only, breach it, see where it goes to define a maximum extent of inundation. Even if it's a tailings dam, kind of defines for you the ultimate if the tailings were all fluid or water only, and maybe bulk it a little bit, and then tailings only, that there's no water at all. Then vary the tailings concentration, vary the X concentration in contot data file. Try a couple of different rheology relationships. I recommend Glenwood number 4 in my mudflow guidelines, simulating mudflow guidelines. Glenwood number 4 gives you a sample that's like wet cement. Vary the sediment transport equations, try a few different ones. Vary the N values downstream, maybe plus or minus 20%, and see if the flow goes a little further or whatever. So as a final product, make sure you're conserving sediment, volumes from your dam breach or tailings dam breach. If you use the tailings dam breach tool, and you're not going to model the actual tailings dam breach itself, and you just want to impose the inflow hydrograph on your downstream reaches of your dam, then that's fine. If you're going to breach it, and in the model like I just showed you here in the example, then the tailings dam breach tool will give you that estimate, and you want to match that estimate with what volume I showed you in that summary.out file. Make sure that they match for the tailings dam, for the tailings breach material in terms of the volume. Do a water only, tailings only again. Make sure that you have reasonable maximum velocities even through the breach, and fluid numbers. If you have a mud flow going, your fluid number is going to not get much above 1 because it's just too viscous, and you're not going to see a lot of hyper concentrated sediment flow, mud flow type of supercritical flow. On the other hand, if it's a mud flood or varying around between being a mud flood and a mud flow is in my table there, you can get some higher fluid numbers, but I still wouldn't get much above 1.5 or 2, something like that. If you have some high maximum velocities and fluid numbers, make sure that you slow the model down and eliminate any numerical surging as the maximum velocities may be out of range in the top few in your vel time FP or vel time C files. If the top 2 or 3 have high velocities that seem unreasonable, say 30 meters per second or something like that, which is 100 feet per second. If you're getting something upwards along that high velocities, you want to back it off a little bit, and it's probably numerical surging somewhere. So slow it down, slow the model down, and make sure that then you're getting more reasonable velocities, unless it's right at the dam itself. If your highest velocities are right at the dam, it may be okay. And be conservative. The objective is to either maximize the mud flow depths or maximize the area of inundation. Now, I just got 3 more slides or so. I wanted to emphasize, we have this webinar and all of these tools, other help support tools like PowerPoint presentations and so forth, manuals on the tailings dam tool. And the tailings dam tool is used to estimate the tailings dam release volume. It's based on historic tailings dam failure data. It will predict whether or not a tailings dam failure could occur or not, based on some data in your. This is an event-based type of tool. It predicts the release volume and will generate for you the inflow.data file in terms of a mudflow hydrograph or tailings dam breach hydrograph for you to route downstream. And then you route this downstream without the breach simulation, or you do the breach simulation and you just match the volumes. So what this looks like, this tailings dam tool, I'll just show you a slide or 2 here, is that you have 3 types of failure modes: hydrologic, static, and seismic. You enter some simple data like the storage, does it have a spillway, and so forth. You enter this simple data, select the different type of failure mode you want, enter the data that occurs on each dialog box, and then it will create or generate for you an inflow.data file. And the data files will be both a hydrograph and a similar set of these for sediment concentration as a function of time. So you can, here's the volume that the model predicted from the breach. You can put in the entire time of the event, say 1 hour, a porosity, a given maximum sediment concentration, and you want the output either by volume or by sediment concentration by volume, and then select the shape. So you can select some different shapes and see which shape of the hydrograph will give you the worst area of inundation downstream. So this is the volume is generated by this tailings tool. You select the failure duration, you select the maximum sediment concentration you're going to have. That it's going to look like a hydrograph like this. I just didn't load any of these. I just didn't show you this plot. I should have probably. It will generate for you the Flow2D inflow hydrograph. You select the grid element, and then it gives you this hydrograph here. And it has time, discharge, and sediment concentration that's generated by this tool. And you just input this file to your project folder and then run it to route the tailings dam breach downstream, or run it and see if you can generate a similar hydrograph or at least get the volumes to match. And so that's the end of my PowerPoint presentation. I'm ready for questions. Let me go to the question panel here and stop the recording. Oh, maybe I did. I don't